We have already learned about outliers. In this video, we shall learn about one extra property that an outlier may or may not have. Suppose we have a scatter plot like this. We have got 10 points and they're pretty much on a straight line, and this is the least square fit. Now suppose we add one more point, this blue point, which is an outlier because it is far from the bulk of the data. The bulk of the data is here and this point is here. And observe that the resulting fit, which is shown by the red line, has swung a lot from this black line. So because of this single point, the least square fit is now ignoring 10 points. So the 10 points all indicated that the line should be like this. Because of a single point, that line swung from this good fit to a rather bad fit position. We will call such a point an influential point, which has so much influence that it outweighed 10 points. Now observe that this was an outlier which was pretty far from this black line. So this was more or less the distance if I consider the vertical distance. Now suppose I take the outlier here. Again, this vertical distance is same. Whatever we had there, we had still the same thing. But now the resulting line is essentially ignoring this point. It is still adhering to its old position. So now the importance is given to only the bulk of the 10 points. Here we say that this outlier is not an influential point. And this example shows that the influence is not directly dependent on only the distance of the point from the original fit. So in both the cases, this distance was the same. The discussion that we are going to do in this video is based mostly on this book. The book by Belsley, Kuh and Welch. It's on regression diagnostics. You will possibly take a closer look at this book during your MSTAT days. Now, as the name of the book suggests, this discussion pertains mainly to the situation where you are in the regression setup and not in an ANOVA setup. So the inputs will be considered to be continuous. Even if there are some discrete inputs, we shall focus on only the continuous inputs. Now, whenever we do any such thing, any such fit, what we do typically is this. We have some data set. So the data set takes the form of a data matrix. It has got the various columns are the variables, including the responses and the predictors. And based on that, we get certain outputs, which are more or less these four quantities. We have the coefficients that we fit, the fitted value themselves, the y hats. So these are the beta hats, the y hat, the residuals, y minus y hat, and the covariance matrix of the coefficients. I'm not talking about the covariance structure here. I mean the covariance matrix of the estimated coefficients. That is sigma square x prime x whole inverse, that thing. So these are the four quantities of primary importance. And we will say a particular case here, all the rows are the different cases, the particular cases here, one case is influential if omission of that makes a drastic change in any one of these four things. So if you find, if I keep it or if I do not keep it, that one case, it changes the estimated coefficients a lot, that is, for example, causes the line to swing a lot, then we say that particular case is influential. Similarly for the other three things. In order to find this out, we use what is called delete one out technique. Namely, we really delete one of the rows. Suppose we take the ith row and delete it, and then again refit the entire model and see whether the resulting coefficient or the fit or the residual or the covariance matrix, the estimated covariance matrix, has changed or not, and how much has it changed. Based on that, we try to measure the influence that particular case has. In this discussion, we are going to need a number of quantities frequently. So let's get acquainted with them. We have this model y equal to x beta plus epsilon, and we are going to fit y hat. So y hat equal to this thing. Now this matrix, this thing from x and going all the way up to x prime, that's a matrix which is basically the orthogonal projection operator onto column space of x. We generally call it the hat matrix. Hat because it puts a hat on y. So if you multiply y with h, it becomes y hat. So we call it the hat matrix. The diagonal entries of this hat matrix are going to play an important role in the discussion. We call them hi. It is the ith diagonal entry of h. We are not calling it hii, I just call it hi, and these are commonly called the hat values. Now we are trying to delete one row at a time and see the effect on the various aspects of the fit. Accordingly, we define xi to be the ith row of x. Remember that xi is a row vector. So if x is n by p, it is a 1 by p vector, a row vector, a horizontal one. And if you remove that, whatever remains of x, that n minus 1 by p thing, that I will denote by x, then round bracket I. It is x without that xi. Everything else in its place, you have just deleted the ith case. Now if we do the fit based on only that x round bracket I thing, the resulting fit I will denote by beta hat round bracket I. That's a vector, a p-dimensional vector. This I means which one has been dropped. Similarly, sigma square hat I is sigma square estimated based on all but the ith case. Now the first thing that we are going to discuss in terms of the effect of deleting the ith row will be on the betas. The resulting quantity we will call df beta. I have called it df beta I, so that subscript I means I have deleted the ith row and I am saying what is the effect on the estimated value of beta. So it is defined in this simple way. You take beta hat, the fit that you obtain from the entire data, then you also fit the same model on the deleted thing and you get beta hat I. You take the difference between them, you call it df beta I. So if there are n cases, then you have df beta 1 to df beta n. Now these quantities, you want to naturally say if this is large, then that point is going to be influential. But as we all know, just to say something is large is not good enough. We have to take into account the variability of this quantity. That is, we should somehow standardize it by dividing it by its some measure of dispersion. So if I divide it by its standard error, in that case we get what is called df beta s. Now the different quantities, remember this is a vector, so it's different components, so you'll have different amount of variability. So you have to divide it by a different quantity. That is why I have called them df beta sij. Remember df beta, these are all vectors, p-dimensional vectors, and these are all scalars. Now I have unpacked them in terms of their separate entries because I need different scaling factors for the different entries. And this quantity downstairs is pretty obvious. We already know that sigma squared times x prime x inverse is the variance, is the covariance matrix of beta hat. So what I do is that I take its jjth entry, that is the diagonal entry, which is sigma square times x prime x inverse, its jjth entry. I take its square root, so this is sigma. Now unfortunately I do not know sigma, so I have to estimate it. I use the deleted estimate of sigma, and that is natural because when I am removing the ith row, it is basically that I am suspecting that it might be too influential. So keeping that in the model might give me misleading estimates, and that is why when I need a reliable estimator of sigma, I am not using that particular case. So in place of sigma, I am plugging sigma hat I. So this quantity is called df beta Sij. So this is basically a matrix. This is the ijth entry of that. This matrix is of the same size as your X matrix, n rows and p columns. The next quantity of importance will be the fit. We similarly want to know whether deleting the ith row will influence the fit or not. So for that we define analogously df fit I, which is y hat I, which is the ith fitted value, minus, now there's a subtlety here, we are again using the ith fitted value when we are not using the ith observation. So in this case we are just taking the ith fitted value, the ith entry of y hat, but in this case we do not have the ith case. So now we are trying to predict the value for the ith case based on the remaining n minus 1 observation, that is this quantity. And this difference is df fit I. Now again, as before, if this quantity is large, then we suspect that this observation has too much influence on the fit. Now, how do you measure that? For that, you have to first do our standardization. The standardization here might look a little tricky. The numerator is this quantity, but the denominator is sigma hat I, then square root of hi. Hi is that hat value, the ith diagonal entry of the hat matrix. Why exactly we divide by that? You may take some little time to figure out that that is nothing but the standard error of the numerator. Just do a little bit of algebra and you will see that. Again, I need sigma here, but since the ith case is a suspect, I am estimating sigma based on all the other n minus 1 cases. The next quantity of interest will be the estimated covariance matrix, that is the standard error matrix, so to speak, of beta hat. So in this case, it is slightly tricky because that's an entire matrix. So again, we have the same idea. We will take that matrix, that is sigma square x prime x inverse, in presence of the ith observation, the ith case, and also in absence of the ith case, but those are two positive definite matrices. How are we going to compare two positive definite matrices? There are various ways that are possible. Possibly the simplest of them is to take ratio of their determinants, and that is precisely what we have done in this particular case. We call it cov fit I. This thing you can easily see is sigma square x prime x inverse. These two vertical bars denote determinant, and I am using all my observations. So in presence of all the observations, this quantity is just the analogous thing, but in absence of that ith row. And I am using sigma square hat without that ith observation, and all these x's are also replaced by x round bracket I. And again the same idea, if this quantity is far from 1, because if it is close to 1, because this time I am taking a ratio, that reference value should be 1. If it is far from 1, we suspect that this is a very influential point. Now how we use that, we will see the details when you see an art session. The final quantity that remains to be discussed is the effect on the residuals. Now, since we have already taken care of the effect on the fit, so there is hardly anything left about the residuals except one thing. When we look at the residuals, we must not forget that the residuals all have different level of variability. So it's a good idea to divide the residuals by their standard deviation or estimated standard deviation before we really look at that. So that is the idea of studentizing the residuals. Now when you do that, when you divide by the standard deviation of a residual, that will involve sigma square. So you have to use sigma square hat for that purpose. Now if you believe that the ith observation is going to be a suspect, then naturally you should not use that observation when you are doing this studentization. And this introduces this definition, which is called R student. R student I is the ith studentized residual. It is defined as yi minus yi hat, that usual residual for the ith case. But when I divide it by its standard deviation, again a little bit of algebra would convince you that the standard deviation is sigma times square root of 1 minus hi. Hi is that hat value. When you divide by that, remember to estimate sigma by not sigma hat but by sigma hat round bracket I. That is called R student I, and that will enable us to get a better idea of the underlying unobservable epsilon i's. Now, all through this discussion, it might seem that we need to fit and refit the same model again and again, dropping one row of your data at a time. That will be prohibitively computation intensive. But in practice, you really do not need to refit the model. You can do some algebraic jugglery so that you fit the model only once, and then from that you can conclude what happens if you drop that ith row from the data. Now, all these details are given in that book by Belsley, Koo and Welch. I am not going to go into all those details. You can work them out quite easily. They are not very inaccessible or anything. But in practice, we shall always use some software like R to compute these quantities for us.